So my goal today is to introduce these ideas of normal surfaces that Haken used so successfully for a wide range of three-manifold algorithms. So I'm going to try and introduce them from scratch and take you through the main ideas of the algorithm. And in particular, the algorithm for recognizing whether a knot is trivial. So we saw some approaches to this unknotting problem yesterday based on computing invariants or simplifying diagrams. Haken's algorithm is a little different in that it's really a three-dimensional manifold-based algorithm. It tries to study this question from the point of view of understanding whether the outside of the knot, the manifold gotten by removing the knot from the three-sphere, is a solid torus. And one way to state that is that we can ask whether this curve that we're looking at and we want to test for knottedness, whether it bounds a embedded disk in its complement. So as I mentioned yesterday, the Dehn's lemma, which was proven by Poincaré showed that the complement is Z if and only if the complement has fundamental group Z if and only if the curve is unknotted, and that's equivalent to having an embedded disk. The problem is the disks that we're looking for might be really complicated. So we're trying to understand these curves, these knots or unknots, by looking for a disk that they span, but we need to have some idea of how complicated this disk might be. So one might hope that somehow there's always a fairly simple disk for any unknotted curve, but that's not true, and I'm going to show you this example. I'm going to construct this example for you a little later this week. There's actually a sequence of, it's possible, and I did this in work with Jack Snoyink and Bill Thurston, it's possible to construct a sequence of knots with n edges, or 11 n edges in this case, with the property that if you tried to fill in this polygonal knot with a disk, so this is an unknot, this is a sequence of unknotted curves, so they all can be filled in by disks which have a certain number of triangles, and you can ask how many triangles are needed. That gives you some measure of the complexity of the disk that fills in this unknotted curve. And for these examples, it's not too hard to show that the number of triangles needed to fill in these unknotting disks grows exponentially, even though the number of edges only grows linearly. So these disks really do need to be exponentially complicated. I'll show you this example. We'll come back to this a little later. Haken's algorithms will solve many problems about surfaces in three-dimensional manifolds, not just the unknotting problem. The unknotting problem, as we stated, is a search for an embedded disk. But there's other important problems that also involve finding surfaces or showing they don't exist. For example, we know now that a three-manifold with infinite fundamental group has a hyperbolic metric if and only if it contains no essential spheres or tori. So we can ask, can we create an algorithm to find such essential disks or spheres or tori if they exist? And it turns out that Haken's algorithm will let us do this. So it's all based on the theory of normal surfaces, which I'm going to give you a quick course on. And I'm going to throw in an even quicker course on integer linear programming today as a bonus, which is the problem that this method reduces to. And in a sense, all of these algorithms based on this approach have two basic steps. One is normalization. We start with a class of surfaces like unknotting disks, and we show that that if they exist, then we can find the normal surface, which I'll define in a few minutes, which is also an unknotting disk. So that's called normalization. And the second step is fundamentalization. In order to get algorithms, we have to reduce this search for an unknotting disk to some sort of finite process. So we'll show that this theory allows us to construct some finite collection of surfaces, which we can explicitly construct, and reduce the search for an unknotting disk or for one of these other surfaces to this finite list, these fundamental surfaces. So the search becomes a finite problem, which we can then analyze algorithmically. So for a warm-up, I'm going to develop the theory of normal curves and show you an algorithm involving normal curves. Now, it's one of the surprising features of many areas of three-dimensional topology, which I think people don't appreciate much, is that how similar it is to the theory of curves on surfaces. In some sense, you'd think curves on surfaces would be much simpler, but and sometimes they are, but often problems about three manifolds, once they're worked out, you realize, looking back on it, that if you had just studied surfaces in the right ways and curves on surfaces, you would have seen what to do in the three-dimensional case. And that's true in this case. If we really understand normal curves on surfaces, then I think that what to do in 3 dimensions becomes quite simple. There's another example. Think about recognizing spheres. Right? If I told you, let's warm up for recognizing the 3-sphere by recognizing the 2-sphere, you might say, well, recognizing the 2-sphere is too easy. You just compute its Euler characteristic. It's a very quick computation. Check that if you have a surface and you check that it's connected and its Euler characteristic is 2, it has to be a 2-sphere. That does not work in 3 dimensions because all 3-dimensional manifolds have Euler characteristic 0. However, there's a more complicated way of recognizing the 2-sphere. Much more complicated in a way, but not that hard. And I'm going to show you that harder way of recognizing the 2-sphere tomorrow, because that will generalize to 3 dimensions. So recognizing the 3-sphere follows by not taking the simplest algorithm for recognizing the 2-sphere, but looking at a slightly more difficult algorithm. So what's the lesson to be learned there? Well, don't always look at the simplest algorithm. Okay, so let's define normal curves. So it's very simple. We take a triangulated 3 manifold. Let's think of it as a simplicial complex. So we've got these triangles, and I've just drawn one of these triangles here, and there's a curve on the surface, one of these complicated curves perhaps. And we look at how these curves intersect this one triangle. And at the left, you'll see some arcs. They wind back and forth a little, but those arcs enter at one edge of the triangle and leave it at another. We'll call those normal arcs or elementary arcs. Those are good. And then there's another kind of arc at the right that crosses itself. We don't want that. Or that doubles back, enters at one edge and leaves at the same edge. Right? So we're not going to allow that in a normal curve. Okay, so a normal curve is simply a curve on the surface, and I've drawn one at the bottom right here with 2 pieces coming through this region. And it just has the property that it always enters and leaves each triangle through distinct edges. Okay, and this idea goes back to 1930. Kneser introduced the notion, and I'll mention later why Kneser was interested in it. Okay, so this is a special kind of curve which doesn't have any of this doubling back. Well, it turns out that you can start with any curve and do a procedure called normalization where you make it normal. So here's the theorem. If you take any embedded curve on a triangulated surface, then you can move an embedded curves until it winds up either being normal or completely contained inside a single triangle. And then we can just erase it. We can consider that we can shrink it down to a point and erase it if that happens. Yes?
Just to make sure your curves are smooth, right, at this moment.
I'm drawing them as smooth. You can think, really, in algorithms, you would make them piecewise linear. But no continuous, no. They're all finite. Other questions? Yeah, I'm not going to do this to a space filling curve or something like that. So here's an example of normalization. We look at the rather complicated curve. It has lots of pieces that loop back in the upper triangle. And I have to be a little bit careful about, I'm going to do this process of isotopping to reduce the number of intersections with the edges by 2. So the weight of a curve is the number of times it meets it meets the edges of a triangulation. And you see there's a red curve there that I can push down. So I go from that picture to this picture, and I decrease the number of intersections with that central horizontal edge by 2 in this normalization process. So I claim I can always do this if I'm not normal, if the curve is not normal. Now you have to be a little careful that you do it on an innermost arc. You don't want to create intersections when you push across, but that's fairly straightforward to do. And so you keep doing it. Each time you reduce the weight by 2, so you must stop eventually. And when you stop, you must be at a normal curve. There's nothing else you could have. And there's a way of thinking about what you're doing, which is very useful for some of the applications we'll be looking at. It'll motivate some ideas for how to approach things like three-sphere recognition. And that is to think about the weight, which is the number of times you cross the edges of triangulation. Think of it as a length of a curve, but not with a smooth Riemannian metric, as we usually think of length, but think of it as some kind of discrete metric, some kind of metric that's completely concentrated along the edges of the triangulation. So as you walk along the surface, when you get to an edge, you have to climb over a wall to get to the next triangle. And you know, it's a lot of work to go over a wall, and it's no work at all to walk on a horizontal plane. So you can actually, this can be made formal, although we'll just think of it for motivation. So I've sort of tried to sketch, not very well over there, what that looks like. You have these triangles with big walls around them, and as you go from one triangle to another, it's like a prison where you escape from one triangle to another, and there's big guard towers at the vertices, so you don't want to stay away from those the vertices. Okay, so the normal curves are just the geodesics in this sort of discrete metric. So here's a little more formal argument. You find the triangle where it's not normal, and you pick an outermost disk, and then you push across it, and you reduce weight. And you see that eventually you either push a whole curve into one triangle or a component into a triangle, or you get a normal curve. So that's normalization. But that was already known. That argument that I sort of indicated for curves was carried out for surfaces in three dimensions by Kneser in 1930. So Haken's real insight was that you could take these normal curves and normal surfaces, and you could assign them an algebraic object. So far, I've just talked about topology and geometry. I've said this is a great way to keep track of surfaces instead of having curves. Instead of having arbitrarily complicated curves, you can just have curves which are, if we look back at these normal curves, they're very simple in every triangle. They're much more manageable as data structures and so on if you wanted to code these up. But Haken realized that these normal curves and normal surfaces also had a very close relationship to certain algebraic objects. And I think this is the real breakthrough or the real insight he had. So the idea is that a normal curve is in one-to-one correspondence with an integer vector, a vector with integer entries in R3T. So a vector with integer entries in a Euclidean space of 3T dimensions. So each triangle, we'll just look at one triangle here. Each triangle is going to contribute 3 coordinates to this vector. Okay, so there's a sort of coordinate for each vertex. Near each vertex of a triangle, I can draw some arcs that go from one edge to another edge near that vertex. And I can draw as many parallel ones as I like, but that's really all I can do if I have a normal curve. So this normal curve, the intersection of this normal curve with this triangle is completely determined by 3 numbers. Right? In this case, 2, 7, and 4. So if we have this integer vector with, in these 3 coordinates, 2, 7, and 4, we know we'll draw 2 arcs in the left corner, 7 arcs in the bottom right corner, and 4 arcs near the top right. This is an incredibly efficient way of recording a curve on a surface, if you think about it. It's exponentially more efficient than keeping track of the vertices of the curve as it crosses the edges, or thinking of the curve as a polygon. Even for curves in the plane, this gives it a very effective way of keeping track of curves that are very convoluted. Yes?
How do you keep track if a normal curve is completely inside the triangle?
If it's completely inside a triangle, we just throw it away. It's a null homotopic. Right, so the theorem said a normal curve, so it's not allowed to have components completely inside a triangle. Other questions? Okay, so there's already this nice way of encoding a curve. But there's a second, and this is the really amazing part of normal surface theory, I think. You can add vectors, right? And there's no reason to think that adding the vectors corresponding to these curves has anything to do with geometry. But it turns out that there's a very natural operation of adding curves which corresponds to adding vectors. And this is sort of the most amazing thing underlying the theory. So let's get to that. So we have these vectors associated to every triangle. So here we have 2 triangles that are adjacent inside on the surface. They share a common edge. So I've drawn them apart just so you can see each triangle. But in the surface, those 2 vertical edges are going to be glued together. They're the same edge in the surface. And what we'd like to know is, do these vectors that describe the number of arcs of each of the 3 types in each of the 2 triangles, do they come from some curve in the surface? Okay, so if we have a curve in the surface, we can always get a vector. But we're asking, can we go the other way around? Does the vector always give us a curve? And the answer is not always, but yes, if some very simple equations are satisfied, these linear equations. Namely, what do I need to get a curve when I glue this together? I just have to have the same number of endpoints on the left as on the right. And then there's exactly one way to fit them together. So I have for each edge a linear equation. There's 2 kinds of arcs that have endpoints on that vertical arc. And their vector entries on the left are vi and vj. So vi plus vj just tells us how many times an arc cuts that vertical edge. Well, it has to be the same whether you look from the left or the right. So vi plus vj, those two coordinates, have to be equal to two other coordinates that come from the other triangle. So let's look at an example with some numbers. Here we have 2 plus 3, vi is 2 and vj is 3. And on the right we have 1 plus 4. And because those are equal, we can get a curve that fits together nicely across those triangles. And in contrast, well, I'll show you an example where they don't fit in a minute. But let's think about what system of equations that gives us if we look at all the edges. We have 3 t variables, each of which is a non-negative integer. So that's these vi's, that's the system of equation. We get one equation for every edge. So how many edges are there? Well, there's 3 edges for every triangle, but you divide by 2 because it's 2 triangles per edge. So 3t over 2 equations. And you also have some inequalities. vi greater or equal to 0. These are called the matching equations. And any integer solutions of these 3 equations determines a curve on the surface. Yes, question?
Is it a curve or a multi-curve?
Well, I didn't say it was connected. Yeah, could be have many components. And actually, that turns out to be one of the stumbling blocks of the theory, is determining connectedness. So in some sense, determining connectedness is trivial. You just start at a vertex and follow along and see if you get everything. But when you want to do things efficiently, that becomes a big issue. That's one of the bottlenecks of the complexity analysis. So we can add normal vectors in a way that corresponds to vector addition. So let's see how that works. So there's 2 cases. Supposing I have a blue curve and a red curve on the surface, and they each give me a vector, and I want to add those vectors and see corresponding addition for curves. So what we have here on the left is the same triangle. This is one triangle, but I've drawn 2 different curves in that triangle. The first curve, the coordinates of that red curve in this triangle are 0, 4, 0, right? 2 of the edge types are 0. There's no arcs near the bottom right corner. There's no arcs near the bottom left corner in the red case. But there are arcs near the top corner, so there's a 4 there. And at the left, there's a 0, 0, 2. Now, these curves happen to be disjoint. This is sort of the simplest case, just for a little warm-up. So we can put those curves together on the surface and they won't intersect. Right? That's what it means to be disjoint. And you see that the vectors just add. So if you have disjoint curves, adding the vectors corresponds to adding the curves just by taking disjoint union. So that's the easy case. The trickier case is if the surfaces intersect. Let's do another case where they're disjoint first. So here we see a blue curve and a red curve on a surface, and they happen not to overlap, right? I can draw them without them overlapping. That'll happen sometimes. If that happens, then I just take the disjoint union of those 2 curves as their sum, and you see that the number of arcs of each type just adds, and so this is called the Haken sum in the case of disjoint curves. It points us at least in the direction that maybe curve sums geometrically do correspond to vector addition. But now let's take a look at curves that aren't disjoint. Supposing we have a blue curve and a red curve and they're not disjoint on the surface, but they cross. Okay, they'll each have a vector, and I can add those vectors together. And the sum vector will describe some new curve which is embedded. Right? These curves are always embedded, the ones coming from vectors. So I have to somehow resolve this intersection to get an embedded curve. And there's two natural ways to do it. Right? If you want to take a crossing and turn it into, and remove it by smoothing it somehow, there's two choices for how to do that. Now, if you have orientations and so on, we've seen in Jeff's talks that you can choose it to respect the orientation or not respect the orientation and so on. Well, we're not going to pay any attention to orientation. Okay, so how are we going to choose which one of these two crossings to use? Well, we'll use what's called the normal sum or the Haken sum. So here's two triangles, and we have some curves coming through these two triangles and crossing. And there's two ways to resolve that crossing, and I've chosen the one that we're going to use, the normal sum, and that's the curve that I'm going to call the normal sum of A and B. Why did I know to pick that one and not the other one? Well, let's see. What would happen if we used the other one? That's called the irregular sum. Sometimes it's called the abnormal sum. Anyway, or the not normal sum. Anyway, so the problem with this is you do this resolution of the crossing and you get something that's not normal, right? It hits an edge twice. And we want our sums to give us normal curves. So there's only one way to do it. There's never two ways to do it. You can check all the cases, and you'll see that there's always one way to do it that gives you a normal curve, and the other resolution of the crossing will give you a non-normal curve. So that means we have a well-defined geometric operation, and if you look at how edges add, it corresponds exactly to vector addition. Now, I made a little remark here. Sometimes, a little later, we're going to come back and look at this irregular sum, because we do have an option. If we happen to get an irregular sum, we can then normalize again. We can try and flow away the irregularity, and that's going to be a useful thing to do. So let's look at another example. We have a red curve in a triangle and a blue curve in the same triangle. What happens when we add them together? Well, you'll see that I've done the cut and paste to resolve those crossings in such a way that I get regular curves. I get curves that are normal after I do the cut and paste, and I didn't have any choice for how to do those cut and pastes. And I wind up with three arcs in that triangle, which, if I straighten them out, will look like this. And you see you get the vector 1, 2, 0, 1, 2 for the three coordinates, which is exactly the sum of the three vectors that the two vectors that I started with. So this geometric sum is exactly corresponding to vector addition of these vectors. And here's another example. One thing you should notice is I drew this blue guy at a fairly big angle. I could have drawn it parallel to the red guys, but depending on how it goes on to connect in other triangles, I don't really have a choice about how to slant it. So I can't really isotope it around without affecting things in the next triangle. So I can't get rid of intersections just by moving that blue curve around. At least not without messing up other triangles. So I have this intersecting red and blue curve. I resolve the crossings in the only way that gives me a normal curve, and I see that the number of arcs adds just as they do in the vector. Okay, so this is, yes?
I was wondering because, the angle is not apparent from your encoding.
Yes, that,
Tell me how you can see whether there will be such intersections just from discriminatorial.
right. So the point is, you can't actually tell exactly what the intersections are. I have, I can isotope a curve, right? I can move it around inside a surface without keeping it normal. Like I can move all those red arcs up a little bit, and it turns out that I can change the intersection with the blue curves sometimes when I do that. But all those things don't change the normal sum. There's some details that you need to check. It all washes out. So there isn't a unique configuration. Well, is there a unique configuration? I could give you a rule that says, space these points equally along and then equally along the edge and draw the line straight. But it turns out that even if you don't do that, it's all well defined. But you're right, there's some details missing. So we've reduced the problem of finding a normal curve to the problem of finding a solution to the matching equations, the equivalent problems. And now we're in a position where we can take geometric and topological problems and translate them into algebraic problems. So I'm going to do the zero-dimensional unknotting problem. Right? So we're going to take a zero sphere. The zero sphere is 2 points. Right? And I'm going to ask, is a zero sphere, if I give you a zero sphere, here's an algorithm to tell if it's unknotted. Okay, what does it mean for a zero sphere to be unknotted? It means it's the boundary of an interval. Right? So another way of saying that is the boundary of a zero sphere, P union Q, is it in the same component of a surface? Right? If it's in the same component, you can join them by an interval of 2 points. So we have some surface which may not be connected, and we're going to use normal curves to get an algorithm to tell whether 2 points are in the same component or not. Okay, so this is not an algorithm I would recommend you coding up, but it's an example of something that's by no means the simplest algorithm, but it will generalize to higher dimensions, unlike the simplest algorithms. So I have 2 examples, one on the left where the answer is yes, P and Q are in the same component, and P union Q is an unknotted zero sphere. And on the right, we have a different surface which has 2 components, a blue and a green component, and P and Q are in different components, and there's no way to join them by an interval in that surface, by a path in the surface. So let's describe an algorithm which will give us yes for the surface on the left and no for the surface on the right. Well, by what we said, an equivalent question to whether there's a curve joining P and Q is the question of whether there's an integer vector in Z 3t coordinates, 3 for every triangle, which satisfies the matching equations, Vi plus Vj equals Vk plus Vl, 1 for each edge. All the variables have to be non-negative. And now I'm going to throw in some extra conditions. So these equations are the equations that describe all normal curves. I want a special kind of normal curve, one that joins P to Q. So I'm going to say, just to be a little concrete, I'm going to say V3 is that red edge that comes out of P, that red normal arc that comes out of P there. I'm going to call that V3. And I'm going to be looking for a normal curve that has V3 equal to 1, and also another normal curve that comes out of Q, V15 I called it, just picking arbitrary examples. So maybe if I can find a normal curve where given by a vector where V3 is 1 and V15 equals 1, then I'll know that this normal curve has 2 boundary points, one at P and one at Q. How do I stop it having other boundary points? I don't want this arc, I don't want my solution to be 2 arcs. I want it to be a single arc. So I'm going to set all the other boundary arcs, all the other normal arcs that hit the boundary equal to 0. I'm going to throw in some extra equations. So I don't know if that's visible, but there's some dashed arcs that hit the boundary, representing normal arcs. And I'm going to set the variables corresponding to each of those equal to 0. And same thing for the other example, where P and Q are in different components. So we have a red arc here. I'm going to set that equal to 0. I'm not going to let my normal curve. I'm going to look at vectors that don't use that normal archetype. But the other archetypes, like this blue one over here that doesn't hit the boundary, I'm going to allow my normal curve to hit there. So we're looking for a vector with certain coordinates equal to 0 and certain coordinates equal to 1. And if such a vector exists, then we can reconstruct a curve that runs from P to Q. So in this case, we can do it. You can see the example right there. That's a normal curve, and it has certain coordinates. There's a certain vector corresponding to this curve. And that vector solves the problem of, that is an unknotting arc for the zero sphere we looked at.
So in your other example, there wasn't a solution?
No. Why? Because
Why can't you kind of come back around? You're just looking for a curve.
I'm looking for.
It's connected. So blue and green are.
Actually, I didn't say it was connected. Well, maybe I did say it was connected. But I don't have to assume that the vector represents a connected curve because arcs have two endpoints.
The triangulations are isomorphic, but the colors are different.
They're not. Are they isomorphic?
Blue and green are actually two different components of the same surface.
Yeah, that's right. There's one surface is on the top row. The second surface is on the bottom row. Yeah, maybe my color scheme isn't ideal. I should have made the bottom one green and for both, I guess. Okay. Next talk. So there's no solution here because there's no arc that starts at P and ends at Q. It has to end. An arc starting at P has to end somewhere, but there's no place it can end. So this was just an example. So in general, if we have some triangulated surface, maybe connected and maybe not, how do we decide if there's a vector solution, an integer vector solution to this problem? So how do we decide if there's an integer vector with certain entries equal to 0, certain entries equal to 1, and so on, by some finite algorithmic procedure? Well, if you're in certain areas of mathematics, you don't have to think twice because you use these methods. This is a standard problem in integer linear programming. When you have integer vectors with linear equations and inequalities, it's called, this was a problem that was studied by Hilbert, who solved it. He showed that there's always a finite basis called the Hilbert basis in the theory. He was using it to study ideals of Noetherian rings, but the ideas exactly translate into general algorithmic settings. So I'm going to give you a 10-minute course in integer linear programming. So this is a little diversion from the main topic, but since it's an important part of these algorithms, and since a lot of people aren't familiar with it, I thought it's worth talking about it. I think that Haken essentially rediscovered it in his arguments because he doesn't refer to Hilbert's work, as far as I know. So what's the idea of integer linear programming? Well, the idea is we have a finite dimensional space, like Euclidean space of d dimensions, and then we have a collection of linear equations like vi plus vj minus vk, like the ones we have, but anything with integer coefficients would work fine. And we also will require that the entries are greater or equal to 0. The theory handles more general things, but for what I need, it will require that. That means that the solutions, notice that the set of solutions forms a linear subspace. The sums of solutions and scalar multiples of solutions are also solutions. So the set of solutions forms a cone, what's called the Hilbert cone. And the positivity assumption means that it's a pointed cone. It doesn't contain any infinite lines. It only contains rays. So what can we say? Let's look at this situation a little more carefully. Hilbert's theorem essentially implies that when you have such equations in RD, and you're just looking for integer solutions, you're not looking for real solutions. So if you've heard of real linear programming, which is the simplex method and so on, involves finding real solutions. And algorithmically, that's much easier. But in this case, the fact that you're restricted to integer solutions creates some computational difficulty. So the theorem says that you can find finitely many fundamental solutions to these equations. So in our case, it means that there's finitely many curves on any surface. You take a surface and take a fixed triangulation, then you can find finitely many curves, f1 up to fk. And what's more, you can actually construct these curves explicitly. There's a procedure you can go through which in a certain amount of time, and how long it takes is important for the complexity analysis, but in some finite amount of time, you can construct all these solutions, and then any solution at all, so any curve at all on this surface, will be some integer linear combination of these fundamental. So that means that any normal curve at all can be gotten from some finite collection of curves by taking multiple copies of them and then taking this geometric sum operation that we talked about. So I thought that, if it's hard to draw these examples without losing what's going on. So I tried to construct the simplest possible example that captures what's going on in this situation. And if you follow through this example, I think you'll really see all the ideas behind Hilbert's theorem. So the example, we're going to start with R3. We're going to start with a three-dimensional vector space. And we're going to look for integer linear solutions to some equations in R3. And the problem is every time I add an equation, I lose a dimension, right? And I don't want to lose too many dimensions. So I'll just take one equation, V3 equals 0. That puts us in the plane, right? So now I can draw the picture. So there's one equation, V3 equals 0. It's an integer linear equation. And then there's some inequalities. I'm going to require everything be greater or equal to 0. But I'm also going to require two additional inequalities. 2v1 minus v2 is greater or equal to 0. So that means that we're below that upper blue line, right? v2 is smaller or equal to 2v1. And the other inequality, 3v2 is greater or equal to v1. That means we're above the lower blue line. So we're in this cone, this green cone. And what we're looking for is integer solutions. So in our situation where each integer solution to these matching equations gives us a curve, each one of the black dots that falls inside that cone will correspond to some curve on the surface, some embedded curve on the surface. And this is quite a complicated lattice. It doesn't have any, I don't think it's completely obvious that it's generated by finitely many solutions, but here's the argument that it is.
Just to understand, so first you have an equality which is 2v1 equals v2.
It's an inequality.
And then you change it into an inequality? I mean, because in the original problem, in the matching.
Let me explain that. You're right. I just had inequalities xi greater or equal to 0 and then in the original formulation.
Right, okay.
But this Hilbert's theorem works for any integer inequalities. And in order to get an interesting example, I had to do something like this. So how do we see that that these black dots inside this cone are sums of some finite collection of fundamental solutions? So the idea is you first add another condition. You projectivize, you look at the plane v1 plus v2 plus v3 equal to 1. So you cut off this infinite cone with this plane, and the intersection, of course, here is just some interval. In general, it's some finite dimensional polytope. So let's do that. We've added this extra condition, we've added this extra equation, and now that we've added this extra equation, we can solve for these intersection points u1 and u2. These are called the vertex solutions, the rational vertex solutions. So let's do that in our case. Let's see how you solve for u1 and u2. So u1, for example, so these are vertex solutions. In general, if I look at this polytope, it'll have faces of various dimensions, and the vertices of this polytope will correspond to lines in this cone. And so we can solve for where those lines intersect that plane that chops off, that projectivizing plane. And in this case, we just look at the equation 3v2 equals v1 and add the equation v1 plus v2 plus v3 equals 1, and v3 is equal to 0, and we see that we can immediately solve for u1 and u2. Okay, so u1 and u2 are not integer solutions, they're rational solutions. They're rational because we solved a system of integer equations to get them. But we can get integer solutions just by clearing the denominators. So in this case, we get integer solutions w1 and w2. Okay, so there's the first two explicit solutions we found. We've now been able to get explicitly at least two solutions. But unfortunately, not all the solutions are linear integer combinations of w1 and w2. So I've drawn in red here the ones that are integer combinations of w1 and w2. And we get some of the solutions that we want to find, but not all. It is true that everything is a rational combination of w1 and w2, but not an integer combination. So how do we get these fundamental solutions? Well, what we do is we look at the parallelepiped spanned by these wi's, these integer solutions that we found so far. And that's some compact region inside this cone. And the fundamental solutions are all the entries that lie inside this parallelepiped that are fundamental. So the definition of fundamental is that a vector is fundamental if it's not the sum of two other vector solutions. which are non-zero. And the claim is all of those fundamental solutions lie inside these, are among the lattice points that lie inside this parallelepiped. So let's see why that's true. Let's take right, in this case, if we look inside that parallelepiped, there was 8 or 10 of these lattice points in there. Not all of them are fundamental. For example, if you look at little f4 there, little f4 is 2 times capital F1. But the capital F's are all fundamental. How many are there? There's 6 of them. So the claim is that there's exactly 6 fundamental solutions for this problem, and every vector, every one of these black dots that lies inside the cone is a linear combination of those 6 fundamental solutions. Let's see why. So let's pick a vector v, like this one I just picked out there. Did you see that vector v there? And why is v a sum of fundamental solutions? Let's see why. Well, v does not lie inside that parallelepiped. The parallelepiped was defined to be all rational combinations. The parallelepiped was all lattice points which are combinations of W1 and W2. Each of his coefficients is smaller or equal to 1. That's what a parallelepiped is. So if V lies outside that parallelepiped, it's a rational sum, it's a rational combination of W1 and W2. One of the coefficients must be bigger than 1, or it would have been inside the parallelepiped. In this case, it's the coefficient of W2, which is F3. So we can subtract one of the vertex solutions. We can subtract W2 from V and land inside the parallelepiped. Well, that means that V is equal to F3 plus something inside the parallelepiped, and the things inside the parallelepiped are all sums of fundamental solutions. Well, that's it. That was, I think if you understand that example, and I know I went through it too fast, but if you look at some example like that, you'll see all the ideas involved in integer linear programming in this part of it. I wouldn't say for the whole subject, but maybe for this particular theorem. Okay, so the takeaway is that when we have the integer vectors defining normal curves, we can explicitly construct some finite collection of fundamental normal vectors, and any normal curve will be a sum of those finitely many. So maybe this is a good time to stop for some exercises. Okay, this is supposed to be a class, so time for a couple of exercises. This is Saul's 5-minute break. Okay, so this is a triangulation of this tetrahedron. It gives a triangulation of the two-sphere with 4 triangles. There are many, many normal curves on this triangulation, but I claim that 7 of them are fundamental. So can you see which ones are fundamental? So one way to do this would be to say there's a system of 12 systems of equation in R12, right? There's 4 triangles with 3 variables each. So you could set up a system of 12-dimensional equations. You'd have each edge, so there's 6 edges, so you'd have 6 linear equations, and 12 variables, and you could actually work through the theory to see what the fundamental solutions are. But we can just see it a little more easily. So claim is there's 7 fundamental curves. There's 4 that are vertex linking, the 4 little circles that just go around the vertex. Why are they fundamental? Why can't they be a sum of 2 other? So they have vector, their vector would look something like, well, in one triangle they'd have a single edge type, and then maybe in the next triangle they'd have some edge type, and these come in groups of 3, and maybe nothing in the next triangle, and then something in the last triangle. So can that be a sum of 2 solutions? Right? Any solution has to have at least 3 arcs, right? Because if this was a sum of 2 solutions, one of them would have, as a vector, one of them would have a single one, and the other one would have 2 ones. If it's non-zero, if they're both non-zero, and 1, 1 just gives, that doesn't give you a closed curve. This is not a sum of two solutions to the equation. So these must be fundamental, these 4. And similarly, the 3 types of quadrilaterals must be fundamental. That's a convenient way of drawing the triangulation of the 2-sphere given by a tetrahedron, which just makes it a little easier to see what the curves are. But this curve is not fundamental, so here's exercise 2. What 2 fundamental curves is that the sum of? This is an octagon. It has 8 edges, this curve. It's a normal curve, right? It intersects every edge, every triangle, and it doesn't double back through any edge of a triangle.
Isn't there the one that goes like that?
What's that?
Isn't there the sum of this?
The sum of, so this is,
That's
we'll call this a rectangle because it has 4 edges. Right?
yeah, and maybe the other rectangle that goes
Okay, let's see.
along the negative side. Maybe not.
Let's see, let's try it. So we're going to do geometric sum in real time now. Let's see if I can draw it the way I drew it there.
No, it's not the right.
So what's the second fundamental one? You have 6.
I have, right, so there's 4, right, there's 6, okay, so the question was, what is the other I said there were 7 fundamental ones, but I only drew 6. So there's 4 of these vertex linking ones, and the way to think of a vertex linking curve is it separates one vertex from the other 3, right? And there's also this kind that separates 2 vertices from the other 2. And there's 3 of those, right? Because there's 3 pairs of 2 vertices. I only drew 2 of them. But there's another one which goes around that edge over there. So let's see. So here's and I think your suggestion was to take this one and can you see these colors? Is this maybe not? Right. So
The one I had in mind first was.
so stick with this one. So that's two fundamental surfaces. And what happens? Let's add them together. Let's practice, right? So what do we do at this crossing when we add these together? Which way do we resolve it? We have a choice. We could either go like this, or we could go like this. This is not good, right? It gives you a non-normal curve. So we have to go like this. And then there's another crossing here. And which way should we go? Well, we can't go like this because then we hit this edge twice. So it must be the other way. Uh-oh. Let's see, what happened? Oh yeah, that's right, that's what we wanted. We got the octagon as a sum of two fundamental. Okay, all right. Yeah.
How do you get, so you have 4 curves going around each vertex, but only 2 going around 2 of the 2 edges.
Right.
The other by summing one vertex, one around.
No, I said there were 7, but I only drew 6 because I ran out of room. There's another one which I should have drawn. There's a 7th. There's three of this type. I only drew 2.
But there's more than 3 edges. So what?
Oh, there's 6 edges. But this one, I've drawn it like it's associated to this edge, but it's actually equally well associated to this edge. It's disjoint from exactly 2 edges. The edges come in pairs and it separates those 2 edges. There's no orientations. Oh, yes, question?
You mentioned the complexity for finding the fundamental solution.
Yeah. Oh, do you want to know what it is? So it's exponential in general. Yeah. But many times there are tricks for improving. So this is exactly what Ben Burton can tell you about. He wrestles with searching through these fundamental solutions. And, you know, for example, in many problems you can show that special types of fundamental solutions, these vertex solutions, it's enough to look at those. There's still exponentially many, but fewer. And sometimes you can even hope to do a little better. But I'll talk about actually the complexity of counting these fundamental solutions a little later, because that's the basic question in the complexity analysis. We've essentially done all the work. We had to solve some system of linear equations. All we have to do is look at the matrices that we used to solve those and see how big things get. That's going to be our complexity analysis. Okay, so am I out of time? Let's see, when do I finish? Oh, I have another 20 minutes. Sorry. Okay, so this is a summary. We've shown that you can go from normal curves to normal vectors, that all normal vectors are some of these finitely many Hilbert basis vectors, and that if a solution exists for a problem we're interested in, such as if a curve bounds a disk, an unknotting disk. Another interesting question is if you have a link, a knot with several components, a link, you can ask, can you pull apart the 2 components of the link? Is there a splitting 2-sphere? A 2-sphere that contains one component of the link inside it and another one outside it. So if you ask these types of problems, it amounts to finding certain types of surfaces. And Haken's idea is, well, first let's show that if such a surface exists, then we can find the normal surface with that property. I haven't defined normal surfaces, but I will. And then show that, so that's normalization. Then step 2 would be, let's show that if there's a normal solution, then one of these fundamental solutions solves our problem. That's fundamentalization. And then the algorithm reduces just to constructing and checking this finite collection of fundamental surfaces. So this same basic plan will just solve a lot of three-manifold problems for us. So let's get back to this. We saw before that if there was a curve connecting P and Q, then there's a normal curve connecting P and Q. What's more, we can pick that curve to have coefficients V3, the one leaving P, set that equal to 1, V15, the one entering Q, set that equal to 1, and set all the other coordinates hitting the boundary equal to 0. That's the problem, the algebraic problem we're going to try and solve by an algorithm. So here's the algorithm. The equivalent problem to is this zero sphere, the trivial zero sphere, is to ask if there's an integer vector with these properties. So here's the algorithm. We're going to construct all the fundamental solutions to this, for this surface with this triangulation. Then we're going to check whether any of the fundamental solutions satisfies these properties that we're interested in. V3 equals 1 and V15 equals 1, and all other variables meeting the boundary are equal to 0. So we're not going to impose those conditions as part of our equations, our linear equations, or we'll lose the linearity. We're just going to use the normal surface equations, construct the fundamental solutions, and then we're going to check whether one of the solutions satisfies these conditions. If yes, then we'll output yes, and no, we'll output no. So there's one thing we need to check to make sure that this works, and this is what we haven't done yet. We've seen that if there's an arc connecting P and Q, then there's a normal arc connecting P and Q by this process of flowing across boundary arcs if we hit one twice in a row. But we still have to show that if there's an arc, then one of the fundamental arc solutions is equal to that arc that we're looking for. So we're going to do similar things for disks and spheres, but it's easiest to understand for this very simple example. So we know that there's some normal curve, and I've indicated that one at the right here. There's some normal curve connecting P and Q. I'm going to assume that there is a normal arc interpolating between P and Q, the kind we're looking for, and I want to show you that can be found, such an arc can be found among the fundamental solutions, the finite number that the Hilbert basis contains. So we say, supposing we take among all the arcs connecting P and Q, there may be many, let's take the one of smallest weight. So geometrically, we might think, let's take the shortest one. Remember, we thought weight is some sort of discrete metric. So let's take the shortest one, the one of smallest weight, and let's show that that one has to be fundamental. So that's the claim. The one of least weight is fundamental. So let's suppose not. Suppose that A is equal to a sum of two other curves. So this vector can be written as a sum of two other curve vectors. Well, if an arc is the sum of two curves, then one of them has to be an arc and one of them has to be closed, right? Because the endpoints curves have an even number of endpoints. So A has two endpoints. A is this non-fundamental normal arc connecting P and Q. And we're saying if we take it to be of least weight and it's not fundamental, then we can write this we can write A as a sum of two things B and C. A is equal to B plus C. So one of B has to be a closed curve. Here it's the blue one. And the other one has to be an arc which has the same endpoints as A. What's more, the weight of A is the sum of the weight of B plus the weight of C. Right? How many times does B cross the edges added to how many times does C cross the edges? Well, you get exactly the number of times that A crossed the edges. Because to get from B and C to A, you do these switches that take you from one, that preserve the property of being normal curves. You don't change the number of intersections with the edges. So I've drawn these little triangles near the switches to show you how they work. So if this original curve was not fundamental, we could write it as a sum of two things. And they have smaller weight. They each have smaller weight, but one of them also is an arc from P to Q. That's a contradiction because we started with the assumption that we have the shortest, the smallest weight one. So if we take the least weight one, we get a fundamental solution that satisfies our assumption. So it suffices to look for a solution within the finitely many fundamental solutions. Notice we took the regular sum in going from B plus C to A. So I'll just take five more minutes to introduce normal surfaces. That sort of finished our course in normal curves. And everything was very concrete. It's a little harder to visualize surfaces, but all the ideas for the surface algorithms are in here. So when we look at three-dimensional manifolds, it turns out that the study of three manifolds, the key part of it is understanding various surfaces sitting inside the three manifold. The simplest example is the spheres that decompose a three manifold into prime pieces. These are called, well, prime decomposition spheres, I guess. So it's a fact that if you take any three-dimensional manifold and cut it along spheres, you'll do one of two things. That sphere might wind up being the boundary of a ball, in which case you won't have done anything. So you throw away that ball and stick a ball back in to fix the puncture you created. You won't have changed the manifold at all if it's the boundary of a ball. But if that manifold doesn't bound the ball on either of its two sides, then you have simplified the manifold. Now that's not obvious. For example, it's not so obvious that a sphere in R3 bounds a ball on one side. Right? That's actually a non-trivial theorem of Alexander, and it's true for smooth and PL spheres. It's not true for continuous sphere, as if you've seen the Alexander Horn sphere, that can be made into a counterexample. So for smoother PL spheres, though, it is true, and Alexander showed that in particular the three-sphere is prime. So there's no way to cut a three-sphere into two pieces in a non-trivial way. And that means that at least we have some hope that this process stops. If you could cut a three-sphere up, then this process would go on forever, and there wouldn't be any such thing as a prime three manifold. But this gives us some hope. But still, you might think, let's take a manifold. We can cut it up along spheres into two pieces, and then take each of those pieces and cut it up into two non-trivial pieces. And maybe you just keep on going forever. How do you know that you eventually have to stop with a prime piece that you can't cut up? That was the problem that led to the creation of normal surfaces. It was studied by Kneser. And Kneser showed, using a very clever and very simple argument with normal surfaces, much simpler than the integer linear programming argument I showed you, that three manifolds do have prime decompositions. Another kind of surface you often want to cut along is disks. So if you have a manifold with boundary, a three-manifold with boundary, and you can find a disk, a non-trivial way of cutting the manifold open with the disk, that's a good thing to do. It simplifies the three-manifold. So looking for compressing disks, this is the problem that comes up in unknotting, but it comes up in general three-manifold theory too. We can often try to cut manifolds up along incompressible surfaces, like this 3 torus here, which is gotten by a cube, gotten from a cube by identifying opposite faces. This is an example of a phenomena where you take a 3 manifold and cut it open along surfaces until you get 3 balls. So there's many, many manifolds that you can do this to. They're called Haken manifolds today because Haken introduced these techniques to study them. What kind of surface you wouldn't want to look for in 3 manifold theory is something like a sphere with some knotted handles and holes and so on, which are compressible. If you cut a 3 manifold open along general surfaces like this, you'll take something simple and make it more complicated. Well, it turns out that the kind of surfaces that you really want to work through all fit very well into normal surface theory. Surfaces can be very complicated, and normal surfaces give a very efficient method to describe them. So as my last slide today, let me just give a definition of a normal surface. So just like the normal curve was a curve which intersected every triangle in a collection of arcs which didn't double back, which went from one edge to another, a normal surface is going to intersect every tetrahedron in one of 7 types of disks. How many disks do I have? How many different disks do I have in this picture?
How many different types? How many disks?
For you, how many disks? For everybody else, how many types? There's 5 types, right, up to isotopy. Good. Because there's
Out of the green ones, there's 10. They're all parallel to each other.
so up to isotopy, there's 5 different types of disks here, right? Up to isotopy, which preserves the tetrahedrons and the structure. So there's a triangle near every vertex, so there's 4 kinds of triangles. And then there's one kind of quadrilateral type. Now, one way to think about how you get these is to ask how would a plane cut a tetrahedra? And this gives all the possible ways that a flat plane will cut a tetrahedra. There's actually 3 types of quadrilaterals. I've just got 1 type in here. Right? As before, we can separate the vertices into pairs in 3 different ways. And what's interesting is that, well, I can get all 4 triangle types in with any one of the quadrilaterals. We can't fit 2 types of quadrilaterals in at the same time. Right? This is what happens when we try. So the curves for 2 quadrilaterals, the boundary curves for 2 quadrilaterals have to intersect. So you can't get disjoint quadrilaterals into a tetrahedron. All right, so tomorrow I'll tell you the corresponding facts will go a little faster since we've seen this theory already, and I'll show you how you use normal surfaces to prove unknotting, and either tomorrow or Thursday we'll look at recognizing the 3-sphere with normal surfaces also. So that'll be it for today. Thanks.
Are there any questions? So, if you have let's say a surface of genus G with n triangles, how many fundamental solutions are there?
Oh, how many fundamental solutions? So it's going to depend on the triangulation and so on. It's not just a function. Yeah, right. It's going to be exponential in t, in the number of triangles. Yeah.
The other question is, can you use that for counting curves? Can you use this method for counting curves?
For counting curves.
Or multi-curves? Or
I suppose you could, as a function of the length or something like that. You could, yeah. I don't know if the bounds would be useful compared to other methods, but you certainly would get some bounds.
You get the correct polynomial up bound.
You get the correct polynomial upper bound.
Do you?
That's what Sol's. Well, so I've been told. I don't know. Check with Sol later. Other questions?
We have a question. I was wondering, is there a way to tell if a normal curve, say a connected normal curve, is a fundamental solution just by looking at the way it looks? Like for instance, can a fundamental solution intersect an edge twice, for instance? Because in all the examples,
Yeah.
just give an example.
No,
I mean, the fundamental solution intersected the edges only once. In that case, it's here intersect twice. I mean, can we just rule this one out just by looking at the way it looks? Just by saying, here it intersects this edge twice, so it can be.
So unfortunately, yeah, it's not quite that simple because there's exponentially many, so they have to have. It's exponential in t, so they'll have to have very large intersections with edges, high numbers. But given a particular one, you can look at all ways of writing it as a sum and check whether anything. So it's easy to check whether, well, relatively easy in principle to check whether something is fundamental by seeing if you can decompose it as a sum of some two things. So in special cases, it can be very easy. Right?
Is the question, sorry, is the question assuming that you already have a list of fundamental services or that you know nothing about fundamental services?
So the question, his question was, is your question, so your question, the first question was, sorry I didn't repeat it. The first question was, if you have a solution, can you tell whether it's fundamental by some property of the curve?
If you don't have the fundamental solutions in front of you, you can't just see if it.
So the second, yeah. So the second question was, are you assuming that you have some knowledge of the solution, the other fundamental solutions? And the answer to that is.
This exercise to show the surface case that fundamental solutions intersect every edge at most twice.
At most,
At most.
So the claim is that in a surface, every fundamental solution intersects every edge at
Every fundamental solution intersects every edge at
intersects every edge at most twice. Doesn't that mean there's? That doesn't imply polynomially many. Okay.
zeros, ones, and twos.
Okay, I'll have to think about that exercise myself.
Any other question?